Hello, everyone. Welcome back to the AAS YouTube channel. This is the good stuff. We're going to cover a AAS Journal Author Series, and I'm super happy to have Sujay Nair with us today. Hi, Sujay.
Hi,
How you doing?
I'm doing pretty good. How about you?
It's going to be another 112, 113 F degree in Phoenix today, so it'll be nice and toasty. But I'm inside with some cooler air, so that's nicer. What is your geolocation? Where are you at?
Well, I'm located in San Ramon, California.
Okay.
So and we're off a little bit of a suburban area. So speaking of weather, it's pretty nice out here.
Cool. Oh yeah. Yeah, I lived in the Bay Area for a few years, so
Yeah, it's nice.
very good. And I understand that you're still in high school, correct?
Yeah, so I'm going into or at least after summer, I'll be going into the 11th grade at Stanford High School. But yeah.
All right, and so you get the honor of being first high school student on the AAS Journal Author Series. So very good.
Yeah.
What do you like to do for research, Sujay?
Well,
So far, anyway.
Considering research, my general research area, or at least what I've done so far, has been with exoplanets. That would be looking at their transits and utilizing the transit method to learn about the planet, and then traits about the planet, like mid-transit times, and then what can we do with that? How can we better use that? We get a lot of data. Yeah, I guess that kind of leads to this topic.
Yeah, so let's go ahead and get to the research note here. So I'll do a screen share, and we are going to cover transit analysis of exoplanets TRES, TRES-5b, and WASP-43b with the Exoplanet Transit Interpretation Code. So Sujay, take us away.
Cool. So yeah, this was a study that myself and one other, Jonathan Varghese, he's also a student researcher. We did this, I think about a month back. And so the motivation behind this was, well, we have a lot of exoplanet data, and this is all transit data for exoplanets. It's simple to get. Any amateur astronomer can image these exoplanets. And we want to utilize this data such that, well, these exoplanets have mid-transit times, which is essentially when the planet comes in the middle of its transit of its host star. And so, but that mid-transit time changes, well, over time due to the uncertainty in the period. So the error on this mid-transit time will increase, as many periods happen. And so because of this, our whole motivation is continuous observation of exoplanets to update these mid-transit times is really useful, especially for large space telescopes, where it's really, every minute is really valuable. Like, for example, the James Webb Space Telescope that's going to be launched next year. So yeah, that is our general motivation, is that we want to have accurate transit times for all telescopes.
Cool.
So yeah, so I guess in this study, I can start with saying that we chose these two exoplanets, TRES-5b and WASP-43b, mainly because those were really ideal targets for us. And we used the Exoplanet Transit Interpretation Code, which is also known as EXOTIC. So this is the anchor of our study. So this was developed by a group called Exoplanet Watch, which is basically a byproduct of the NASA Jet Propulsion Laboratory.
Okay.
And the project lead, Dr. Zellum, assisted us a lot given just a set of FITS files, we can input it into EXOTIC and get a light curve, which shows the apparent brightness of the star as that planet comes in front of it. So we can see that dip. And so given this light curve and some other parameters that it calculates, we can do some calculations to see, well, how far off was the mid-transit time that we observed from what we see currently, let's say on the NASA Exoplanet Archive. And then we can see, okay, did this mid-transit need updating? And if so, by how much? And then we can then publish those values, which kind of gives importance to this.
Cool.
Yeah, so maybe that is a good introduction. Maybe we can move on to essentially how we got our data. So an amateur astronomer by the name of Pat Boyce, he's from the Sierra Remote Observatory. He imaged TRES 5b for us. It was data that came with calibration frames. Yeah, it was essentially a simple data set. And yeah, so he imaged that target for us, and we used that data when we were running Exotic. For WASP 43b, we, using a student research group code, we requested images from the McDonald Observatory, which was a sub part of the Las Cumbres Observatory, which has a bunch of robotic telescopes. So yeah, that leads into, well, we wanted targets with decently short, short periods and kind of larger transit depths, which were a lot easier to kind of analyze and look for those differences in mid-transit times using Exotic. So these exoplanets met those criteria. So I mean, when it comes to running Exotic, it's really simple. Essentially, we just pointed it to the directory of where our FITS files were. And we were able to run the planets through fully and then get our answers. But we did run into some issues for the exoplanet TRES 5b. For example, we ran into something called a meridian flip, which is where, as the telescope is tracking the star, it comes to a point where the telescope cannot move vertically anymore due to that star crossing what's called the meridian. That's what we say. So then it needs to rotate its base about 180 degrees, such that we can then continue to track it. So that has an effect on the images, which is something that we had to deal with then. So we can talk a little bit more once we get to the observations of it, how we did it. But maybe now I can show a little bit of what Exotic looks like from the terminal.
Sure. Screen share is all yours.
My screen. Cool. So can you see this?
Looks great.
So here we have basically a simple run of Exotic. So I've already entered in all the stuff, but you can see it's run through Python, and there's these, it'll prompt you for certain things like how do you want to reduce your data, like real time, as in you're taking images currently and you're inputting them real time into a folder, or you already have all your data there. And so we already had our data there, so we went for this complete reduction. Exotic also has the option of entering pre-reduced data in a text file, or simply performing aperture photometry. And we could have gotten pre-reduced text file from certain pipelines. In previous studies, we've done that, but here we just went with the FITS files. And then we can choose to make it simpler on ourselves if we're running it many times with using an input file. And so that's what we did earlier. This example is for a different planet, but this is generally how it'll work. So we'll show our inits file. For example, in this example, it's for the exoplanet KPS-1b, but it would be the same for the other exoplanets. So it's going to scrap all these parameters from the NASA Exoplanet Archive, and you can check them for yourself to see, okay, is this what you expect? And so generally, like all these things, they should be fine. This is all from the NASA Exoplanet Archive, so these values should be right. And then from there, it'll just run through it. So now you don't really have anything to do. So one thing to note is in that inits file, you have comparison stars, which is something you're going to compare the relative brightness of your target star to, such that you can negate the effects of the atmosphere. So Exotic you can input as many comparison stars as you want, and Exotic will go through them, and it'll find which one is the best comparison star with the lowest residuals. In this case, it chose, well, this comparison star. And so from there, it'll do an MCMC. At the time of fitting it, when we did our data, Exotic was doing an MCMC diagnostic test for finding these values such as a mid-transit time or air mass constants. But now it uses something much faster nested sampler. However, in the grand scheme of things, the values will be correct. The only difference between the two is timings. So, but yeah, here it was the MCMC. And so after it did all this, it inputs the fitted mid-transit time, the RP over RS, and then all these different parameters, which we can then use and compare to look at that mid-transit difference, a phase difference. So I'll just show what a light curve usually looks like. So here we have a really ideal light curve. This is of the exoplanet WASP 140b, but this is what a general light curve will look like. It'll give you the residuals, it'll give you the relative flux, and you can see it's a pretty clear a dip.
Yep.
So yeah, that's about it for how the software looks. And so maybe now we can talk about what our specific observation was now for Trust 5B.
Okay.
So Trust 5B was interesting in that it had that meridian flip.
Mm-hmm.
So there were many ways to go about this. The way that we chose was Exotic, in addition to outputting these values, it'll output well-produced text files. It'll reduce your data, and then it'll, at the end, even after it gives you a light curve, it'll also throw in like a CSV file with all the flux values.
Okay.
So what we did was we found the image where this meridian flip happened, and we just ran Exotic on before the meridian flip and after the meridian flip. So all the images were constant in the respective runs, such that we would get just the flux files, those pre-reduced files with all the flux values, because that's just the flux values. That doesn't have any. The meridian flip won't have any effect on that. So we just combined those flux values and inputted that as one file. And so then we were able to get this light curve, because at the end of the day, then there's no reduction that needs to be done. It's already reduced. So that gave us what we see in figure 1, that light curve right there. And yeah, it was pretty clean. You can see a clear dip. One other way of getting this was an astronomer by the name of Michael Fitzgerald. He coded up a couple scripts that align images and flip them beforehand, so you can just input them into Exotic. We tested this once, and it gave us about the exact same, like basically the exact same light curve. So either method works. The only difference was when Pat Boyce imaged this for us, he provided additional calibration frames. So when we threw in just the files with the flux values, we were able to add those calibration frames through Exotic. However, when we did it through the images, there were some different shapes of the images because they were being altered. So we weren't able to use the calibration frames then. And now in this case, it didn't make a significant difference. It may in some other case, but here it worked fine, and we were able to get a clean light curve.
Nice.
So after we reduced it all, now it comes to, well, the main idea of the study is we look at the mid-transit times.
Yes.
So we got the mid-transit time from there. We compared it with the mid-transit time on the NASA Exoplanet archive. And with a simple equation, we were able to calculate that had a phase difference of around 12 minutes.
Okay.
So with any respective errors, it might be around, let's say, 10 minutes. So a phase difference of 10 minutes, meaning that the mid-transit time was off by 10 minutes.
Okay.
So we can then publish that saying that the mid-transit time has been updated by 10 minutes. So
and then that result gets picked up by the NASA archive and incorporated into it.
I believe they do some research around that. I'm not sure if it has been updated yet. But I think they also do some studies, but I guess they could, essentially take the value that we have if you just add the 12 minutes to the expected of that night and change the value. Yeah.
Mm-hmm.
But
Okay.
I'm not sure specifically if they have done that.
Okay.
So yeah, that was Trust 5B. That was overall a pretty successful run. We can move on to WASP 43B now. So this planet was different. We got it from Lascumber's Observatory, which we thought that, well, it's coming from a robotic telescope, so the images should be cleaner. We should ideally get a nicer light curve, especially since this planet has a decently large transit depth, around 2.5%, which is pretty large for exoplanets. So we plotted 3 light curves, each with a different comparison star. Though we weren't able to get a clean light curve, or at least of the 3 that were shown, it was like the Exotic fit a dip, but it was not something like, we don't see that 2.55% dip, and the data was decently noisy. So we suspected that the fit was incorrect, or it was possible that the target was not imaged properly. At least from the data that we see, it seems like it's pretty constant. It doesn't look like there's a transit there. So the telescope may have missed the transit,
Okay. No.
but in any case, we still went through with it and wanted to see, okay, what can we still get some phase difference, even though if this is not the most, even if we don't have the most confidence in this value. And then we did calculate it, but we had a huge phase difference of around 8 hours, which was very likely just due to the noise in data and in an incorrect value. So the large difference, this was we weren't sure this was right because, well, the period of the planet was around like 19.2 hours, so almost half the period is very unlikely. We did get confidence in the value of 8 hours because the other two light curves also gave that value, but we doubted it due to the highly suboptimal fit. So in this case, we were able to say that the WASP-43b probably needed more research. We probably want to re-request it at some point, though we suspect that either Las Cumbres Observatory may have missed the transit, or there may have been some error that came up during the fitting, maybe one faulty image or something, because that could throw it off. So, I mean, overall, we weren't too clear on WASP-43b because that phase difference was really large. We thought it was because of incorrect data collection. It could have also been because of a faulty image or some noise of some sort. We were successful in updating TRES-5b's transit midpoint. That was about 12 minutes. And we have high confidence in this because in multiple TRES-5b light curves, we all saw the same phase difference. And additionally, we were also able to account for the meridian flip, which after doing that, I think has brought a little bit more attention to meridian flips and what they do in data, because as of right now, in the most recent update of Exotic, which is constantly being updated by the Exoplanet Watch team, I believe they're accounting for meridian flips by including an aligning script of some sort. So yeah, overall, that is the entirety of the study. For our future work, we definitely want to re-request WASP-43b and want to see what was going on over there. It's likely that the transit WASP-43b is being observed a lot already. And that's probably due to the large transit depth. It is a pretty common planet. We've seen it in other studies. But it's still, I think, overall worth looking at again. But yeah, that would be our future work. And then lastly, we just wanted to thank, we made use of the NASA Exoplanet Archive. Wanted to thank, like, for example, Dr. Zelm, which is the lead of the Exoplanet Watch team. And then, of course, WASP Telescope, and just people who guided us throughout the way.
Very cool. Very cool. Is this your first, was that your first research note?
First research note at the AAS, yeah.
Cool.
Or I remember last year, during the winter AAS in Hawaii, yes.
Yeah.
We were there and we talked a little bit about this mid-transit, but it was more on like analysis of comparison stars and some stuff with Exoplanet. And we did a little poster talk at a workshop then, but it was really cool to be able to write a research note this year.
Yeah, very nice. Do you anticipate deepening or expanding this work to the point where you could submit a regular journal article?
Yeah, so we definitely want to do more vast studies. For example, here we focused on just the mid-transit times of these exoplanets, but I think we could use the mid-transit times and in addition do work on comparison stars, like learn more about the effects of different comparison stars on light curves. Those are always interesting things to look at. Also, you can look at, let's say you can try to calculate the mass or estimate the mass or different parameters for these planets, and then see how those traits like mass or whatever of, other stars affect it. So I think it's a big area, and I definitely want to explore more in this area, try to publish more, because I think the research is definitely really interesting. You learn a lot about these planets and about these systems. But,
Super.
yeah.
Super. Well, I wish you the best with that. That's really good. So Sujay, I want to thank you very much for spending some time today and walking us through your article and walking us through a little bit of how Exotic works.
Yeah. Thank you.
All righty. Thank you, everyone, and we will see you on the next one. Bye-bye.